so this is lecture 2 of our lecture today. Okay, so in the previous lecture we have seen that atoms inside the silicon crystal or any kind of crystal material are regularly placed, and it can be described with two different concepts, like what is the lattice type of our crystal structure, and what is the basis function for atomic configuration. So combining these two factors, we can consider a certain crystal structure. For example, the most important one, the dynamic diamond structure, is just a combination of a face-centered cubic and two atom bases. Okay, so I think that was the most important one, because we must understand the crystal. The essential point of this crystal structure is its periodicity. So periodic atoms are placed in a period way. That is most important one. So now let's go to today's lecture content. So today's lecture content starts from 1D space with a flat potential. So there is no variation, position dependent variation of potential energy. So we call it as a free electron. Here free means that it is not confined by certain potential well. In this case, so once again, this is not not a course for junior students, so I just assume that all of you have already heard about Schrödinger equation or something like that. What is the wave function? That is understood. So we must solve this Schrödinger equation, single electron Schrödinger equation, in order to solve this problem. You know that here we have a certain part corresponding to the kinetic energy of our electron, and of course we have to have another term corresponding to the potential energy. So here we must have another term, so potential energy multiplied by wave function. So combination of these two operators, so where is it? Okay, this operator, so partial derivative with respect to the position, this is corresponding to the kinetic energy, and this one is corresponding to the potential energy. Sum of the kinetic energy and potential energy can be regarded as the total energy of this electron, and that number is equal to certain energy here written as E. So this equation, Schrödinger equation, can be in this form, can be regarded as eigenvalue problem. So by solving this eigenvalue problem, we will find a certain pair of certain energy and corresponding wave function. So it means that this wave function has the energy corresponding to certain value E. So that is the typical way to consider this Schrödinger equation. However, in this free electron case, we assume that there is no potential variation along the x-axis, so we can easily say that, okay, the potential energy here can be regarded as just 0. So that's the reason why we have only kinetic energy term. So now, if you understand this one, then now let's go to the next line here. So here we implement the periodic boundary condition. So we are now considering certain domain. Now let's say that here we have a position x equal to 0 and nz x equal to some number. However, let's say that this is just integer multiple of a certain unit. Here unit length is written as a, and this is quite a short length, and we can consider multiple here, and large n means quite a large number. So for example, you can treat it as, for example, this a number is close to 0.5 nanometer, and you can say that the entire scale is just macroscopic, so centimeter. For example, we have already seen that there can be a cube 1 centimeter by 1 centimeter, 1 centimeter. So typical number of n can be, for example, million or something like that. So, but n is regarded as quite a large number, and a is quite a short length scale. But anyway, now we have a finite length scale. This is not, how can I say, kilometer or even longer. So this number or this length scale is just micrometer, or sometimes around centimeter, something like millimeter, something like that. So here we have introduced the periodic boundary condition. So actually this periodic boundary condition means that if wave touch, oh, where can I find, okay, so the wave function touch this, the last but rightmost point of this domain, then it is entering into the system from the leftmost point. So this is not realistic. Actually, we must consider more realistic boundary conditions at this and that. However, if we consider more, how can I say, more realistic boundary condition, then that will yield certain surface concentrated states. That is not of our interest right now. We wanted to consider certain states which is closely related with its bulk property. What happens if we have a quite large system containing millions or billions of atoms in it? Since our interest is laid on this kind of bulk property, so we wanted to eliminate any kind of surface state. That's the reason why we are justified to use this periodic boundary condition. Since this system is periodic, there is no surface concentrated state, so now we can use this periodic boundary condition. So once we accept this periodic boundary condition, so at two boundary, leftmost boundary and rightmost boundary, they should be the same, then we can immediately understand this is the possible solution. Exponential I k x, and of course k is not any double precision number, any floating number, but we have a certain condition to satisfy this solution. For example, let's say that x equal to 0. Then what happens? So this is just exponential of 0 and equal to 1. And what happens if we go to x equal to, NA? Then we will have exponential of I times, so this NA and NA, both of them are cancelled out. Then we will have 2 pi n, multiple of 2 pi, integer multiple of 2 pi. So it will give us once again 0. So happen to be they are the same. Of course, although we have here number 1 and number 1, this is just for the matter of our normalization. So here we have a proportionality here, not exactly equal, because we can introduce a certain normalization constant. So if A has a certain phase, complex phase, then we can understand this is no longer 1, but it can be regarded as A and A. And anyway, this periodic boundary condition is satisfied by this functional form exponential ikx, and you know that k is not any number, but it should be given by this way. But you know, in the elementary course for quantum mechanics or semiconductor physics, we have already seen a similar problem called as infinite potential wave problem. At that time, we have also similar form like a sine, something like that. However, at that time, this length scale was just a. So size of a certain infinite potential wave. But in this case, right now we are considering n times a, and what is n? N is integer, however, which is much larger than number 1. We are now considering quite a long system. So, you know, this number, this length scale is quite long. So now we can see that the distance between k value and next k value is quite, the difference between them is quite small and can be eventually regarded as continuous number. For example, now think about this one. You have number 1, 2, 3, 4. Okay, this is quite distinctive. 1, 2, 3, 4. And now you have 1.1, 1.2, 1.3. Yes, this is still quite much distinctive, and you can easily understand the difference. Then now let's say that 1 plus 10 to the minus 14 and 1 plus 2 times 10 to the 14, 3 times 10 to the 14. So yes, they are also all different, and their difference is exactly given by 10 to the minus 14. However, if we just visualize them, then what happens? 1, 2, 3, 4, they can be clearly distinguishable. However, if we just draw these numbers, 1 plus 10 to the minus 14, 1 to 2 times 10 to the minus 14, then although they are distinctive, but they looks like just a continuous number. We will eventually follow that description. Okay, the magic comes from the scale of our entire system. If our system is just 1 nanometer wide, then it is no longer possible for us to make it as a continuous. However, if you have 1 centimeter long system, then it is almost always allowed it to treat it as a continuous system. Okay, so although the mathematical point of view, although they are equal or identical, equivalent, but we have different description eventually. So now, by the way, if you have any question, then please interrupt me. I will be happy to be interrupted by your question. Okay, so this is the wave function. So every wave function has its corresponding energy, and you know that in this case energy is given by this form, reduced Planck constant Haba square divided by 2m. Here m is mass, and k is given by this number. So integer multiple of 2 pi over our length scale. So since this length scale is quite a large number, so usually if we have a small index number 1, 2, 3, then k will be quite small. So you can easily understand this one. So therefore, as a last word for or statement in this slide, this k value can be used to identify a state. If you have a different k value, that is corresponding to a different state. For example, all of us have the number assigned to us. For example, in Korea, we have a national ID number, or sometimes all of us have also our own cell phone number. So then using that cell phone number, we can track who is the owner of that cell phone. So simply speaking, if you know a number called as K, then you can find an electronic state. Okay, of course this is 1D problem, and if we go to 3-dimensional case, of course this K should be regarded as a combination of Kx and Ky and Kz, and if you know this triplet of floating numbers, then you can identify, oh, there is a certain electronic state. Okay, so that is possible. So that is all related with the free electron case. So everybody understand the next step will be introducing periodic potential, because we are now talking about the crystal structure and atoms are placed in a periodic way, and if atom provide us a certain potential, then once again the potential will be periodic. So we will see what happens. Oh, so sorry about that. So I have prepared a numerical example for free electron. So I have prepared the A, the unit cell size of just 0.4 nanometer. This is corresponding to 4 angstrom, so atomic scale. Yes, we know it. And N is quite small, like just 40. You expected 1 million or 1 billion, but unfortunately, using my laptop, I cannot perform such a kind of a huge system. So I just restricted myself to just number 40. So we have 40 cells, and I just applied the periodic boundary condition. So now let's have a look at what happens if I just solve it with the computer. Then you get so many different energy levels, but since we are more or less interested with the lowest energies, whose energy, the state whose energy value is quite low, so I just collect 80 of them. Eventually here, since I have used my real space discretization was done with this number. Actually I have 1600 eigenvalues, but I just collected the lowest, the first 80 states. So this is the result. Please have a look at your left figure. So this is the index and this is energy. So index, since they are sorted, so ascending in an ascending order, so you can see that if we go to the higher index, then energy is increasing. What you can see is it follows a parabolic graph. Looks like a parabolic. Good. It is corresponding to our energy versus index related relation. Okay, good. But please have a look at this graph more closely. You can find that there is something weird, although it looks like a parabola, but you know that they are having the same value. It means that actually when we just solve this system, we can find a pair corresponding to a certain energy. If we have a certain energy, then we can find two states corresponding to the same energy value. So I just in the right figure, I just collect only positive numbers. I mean that, sorry about that. Here we have something like this. If we go to very first one, it has energy 0, and the index 1 and index 2 and 3, they have the same number. Index 3 and 4 and 5, they have the same energy. Also 6 and 7, they have the same energy. So in this right figure, I just eliminate duplicated one and just draw one of them. For example, I just took it and eliminated this duplicated one. That is drawn in the right figure, and that is compared with our analytic expression shown here, and you can immediately understand our numerical calculation result is corresponding to the analytic case. Since this system is really simple, our numerical calculation result should be identical or closely follow this analytic expression. So now we are ready to go to other one. Before going to the periodic potential case, let me explain a little bit more about the existence of a pair. Why do we have two different states for a given energy? When I just draw one pair and another pair, the wave function is shown here. For example, this is for index 2 and this is index 3, and this blue one is index 4 and this one is index 5 actually. Yes. So what you can see is actually both of them have the same period, and only difference is their phase. So if you just shift this blue curve toward that way, the right direction, then you can find that actually this blue curve and black curve are overlapped completely. So why do we have this kind of thing? Actually, one of them is corresponding to, for example, cosine. In this example, black one is corresponding to the cosine, and blue one is corresponding to the sine. So when we just make a linear superposition, linear combination of this cosine and sine using certain imaginary number I, then we can construct both of e to the ikx and e to the minus ikx. So since this k is a positive number, this means that the positively moving wave, and this one is corresponding to negatively moving waves. Okay, so you know, in free space, yes, free space, and now let's say that it is moving in this way, positive direction, and the same waveform is moving in the opposite direction. So can we expect any kind of difference in their energies? So no, because it is not direction dependent. So that's the reason why if its energy is given by E, then we can also expect that there will be also the same state but propagating the opposite direction. So that's the reason why we have a pair. Okay, and when you go to the lowest k value, lowest positive k value, and if you go to the second lowest k value available, you can find that actually the second one shows more steep variation, more frequent spatial variation, and you can easily understand if we increase this integer number from 2, 3, 4, 5, then what will happen? Then there will be more and more up and down of our wave function. That is the result of our plane wave or free electron. Okay, do you have any question? Up to now, we have, although our plan is quite much ambitious, but right now we just neglect all kinds of potential effect. So this is just a free electron. The answer is a plane wave, just like electromagnetic wave in free space. So if you have any question, then please interrupt me. Then now let's combine the lessons up to now and our previous lesson in lecture 1. Lecture 1, we have studied that atomic cores are placed in a periodic way. And now also we understand in a Schrödinger equation, we must consider the potential energy. So if atoms are placed in a periodic manner in the crystal structure, and they will contribute negative potentials to our system. Why they have negative potential? Because you know, here if this is silicon core, and silicon core is positively charged and 14 times of unit elementary charge. However, it has 10 core electrons and 4 valence electrons. So taking its second level, and this is the third level. So 10 cores and this 14. So although these 10 core electrons are surrounding this 14 atomic core, but you know, they are not perfectly balanced. Still, they are not exactly balanced in their charge. So if we just collect whether this is negatively charged or positively charged, then we must say that, okay, it is good to say our atomic cores surrounded by core electrons are still being positively charged. So from the viewpoint of our another electron, they are quite much attractive because they are positively charged. So that's the reason why they can be acting as a potential trap for our electrons. So if we go to quite close to the atomic cores, and they are just captured, and this intermediate point is not much prepared by our electrons because they are not, this point we don't have a positively charged state or positive charge. Okay, so now let's just introduce this kind of a potential trap into our system, but not just one single trap, but periodically place these potential traps. For example, we are considering in our example, we are considering 40 unit cells. So I will just introduce 40 potential trap or small wells into our system in a periodical way. Okay, so their potential profile will just look like this, and we can expect that there are 40 copies of this 40 copies of this potential. And finally, still please note that here and there at two boundary conditions, boundary positions, we have applied the periodic boundary condition. Then now let's revisit our numerical example once again. Only difference is we have introduced potential trap, and it is periodic. The unit cell size is the same and number of unit the same. However, I have introduced 10 nanometer long potential well. Please note that. So sorry about that. Well width is not 10 nanometer. This is a serious mistake. Sorry about that. I just introduced 0.1 nanometer. So here we have 0.4 nanometer unit cell, and inside it I just introduce just 0.1 nanometer wide potential well, and its depth is given by, no, in this case its depth is given by 10 electron volt, or sometimes I have used 1 electron volt, but right now this value is given from 10 electron volt. Okay, so if we introduce this potential well, then your result is shown in this left figure, and still we are just showing the very first 80 lowest energy levels. Then please make a comparison between our present result and former result for our free electron case. What happens? Please try to observe the difference between them. So you can first identify, oh, there is a really visible difference between, or jump of our energy levels at a certain position. And you know that here it starts from energy equal to 0, but now it starts from certain energy like lower than minus 4 electron volt, because you know we have introduced two levels, 0 electron volt and minus 10 electron volts. So the lowest one takes the lowest certain energy level in between. That's the reason why the very first energy level starts from not from exactly 0 electron volt, but certain negative value. Okay, so what is your opinion? By introducing certain periodicity, our energy versus index graph is fundamentally changed. So without any potential or without periodic potential, they looks like just a parabola. Everywhere, for example, if we just slightly change our index, mode index, then what happens? Only energy is incrementally slightly changed. They are looking quite smooth. Of course, they are different. Yes, they are different, but since x-axis is slightly changed, also y-axis is slightly changed. But please have a look at this part. Here also we have smooth transition, but in this point here and that, although we have slightly changed the mode index, but they have really big difference. So that introduced by what? By the periodic potential. So that is the point. The reason why we have so-called band gap in the crystal structure is its periodic potential. If we don't have any periodicity in our potential profile, then we will not have this kind of energy difference between two neighboring K points, so there will be no band gap at all. Okay. Then let's go to the further observation about wave function. Yes, I don't remember. Yes, this is the K value, the lowest available K value, like so. The very first one, 2 pi over our length scale, and we have a similar situation, but wave function looks quite much how can I say, much dirty, or not very beautiful, and they show up and down, so much up and down, up and down, up and down. So please note that this is corresponding to the lowest energy. No, this is K is equal to 1, number 1, and its energy is quite low, and wave function formally quite smooth. But when we go to a periodic potential well, what happens? You can see so many up and down. And let's try to count the total number of peaks. Let me do it together with you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, where do we have another peak? Yeah, let's call it as this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Finally, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is total number of peaks in this graph? You can immediately understand by counting them all. This is corresponding to number 40. And what is number 40? In this example, we have used 40 unit cells to make our entire system. Means that this very frequent up and down in real space is corresponding to every unit cell wise transition. So every unit cell, it has up and down. But you know, once we collect these peak values, so let me just do it. If we just connect our peak values only, then we will have, can you see it clearly? So I cannot see actually. Okay. If we just connect only peak values, then you can reconstruct once again very smooth transition, and it looks like, just looks like that of free electron. So now you understand, in a periodic potential well, although our wave function is heavily affected, however, their impact is just a combination of our previous smooth transition and very frequent change due to the unit cell. Okay. Periodicity in our unit cell. So if you have any question, then once again, please let me know. Now I just repeat this observation once again. So our wave function in a periodic potential well is just a modulated version of a free electron wave function. So you can easily understand this one, or check this point by reducing the depth of your potential well. Previously, we have seen the case where potential well is, its height is 10 electron volt. But what happens if I just consider 1 electron volt? Then effect of this potential well is quite much reduced. And what is your opinion about this right figure? You can easily understand, although that is affected by the periodic potential well, but its impact is much reduced. Why? Because our potential well is not as strong as in the right figure. So now let's assume that instead of this 1 electron volt, now let's go to 0.1 electron volt or 1 milli electron volt. then what will happen? Then it will converge to the free electron case. So this modulation, this modulation is solely provided from the periodicity of our potential well. So everybody can understand this one. So up to now it was just one numerical example, and we just make a certain observation taken from numerical example. However, if you go to the more advanced course, you can actually prove that there exists a theorem for this one. Let me just state without its proof. Under a periodic potential, the wave function can be expressed in a form of this one. Oh, this one. The wave function is written as our free electron wave function. However, there is another factor multiplied to the free electron wave function, and this is just doing some job for modulation. But this modulation is not arbitrary, but this modulation is periodic within the direct lattice. So in the case of our diamond structure, it follows the periodicity of FCC, phase centered cubic. So in this simple example of a 1D system, it just follows the length scale of A. Within A, they are just showing the periodicity. So therefore, actually solving or analyzing the electronic states under a periodic potential is not a trivial job, but at least we can have some clues to analyze that problem. Because although this wave function is affected by the periodic potential, but its impact is just limited to the wave function modulation. So, and this is just quite short length scale, atomic unit cell. So in a longer term, or if we go to more long length scale, then its behavior just looks like a free electron. So we can treat our wave function inside the periodic boundary condition. Even in this case, we can treat it as just dressed free electron, just like a plane wave. So that is a really important one, and still we can treat this k number, the wave number. It is called as a wave number, and this wave number, or if this is just a single number, then it is called as a wave number. But in this case, this is a vector, so it is more preferred to called as wave vector. So in one case, 1D case or 3D case, we prefer wave number or wave vector. And anyway, this k vector can be still used as an identifier for an electronic state. So if we know certain k vector in a three-dimensional electronic system, then we can identify one single electronic system or electronic state. And this right figure just shows an example of our u function, how the u function looks like. I just calculated and drawn it, and in this case here we have a position, and this position is, I just drawn only 4 unit cells, because if I just draw all 40 unit cells, it looks so ugly and so dingy. So I just drawn a part of it, And you can see that this U function shows some peak and peak and peak and peak. These peaks are related with the position of our potential well. You can easily understand if we have potential well, our electron try to occupy the position of a potential well. So electrons are more chances to occupy this potential well, and the midpoint between two potential well is less preferred by our electrons. That is written here. So therefore, anyway, in order to clearly identify our electronic system, we must know U and K. However, once we calculate U, and that is just a detail of that electronic state. So if we just view an electron as an object moving or carrying the charge, then actually this K is enough. They are moving, and its wave function is given by this K vector. So if you don't understand, then please once again ask me a question. And before going into the next topic, let me just show the reduced zone scheme. We are working in the reduced zone scheme. However, let's go to the original one. Without using this reduced zone scheme, this is the collection of our calculation result. Numerical simulation just shows this kind of behavior. And where can you find the first Brillouin zone of our system? And this is corresponding to the first Brillouin zone of our system. And where can you find the second Brillouin zone? Your second Brillouin zone is corresponding to this shaded area. And if we go to the third Brillouin zone, then you can see that this, once again, another shaded area, it is corresponding to the third Brillouin zone. So of course we can define so many nth Brillouin zone, then combining from the first one to nth one, then our K space will expand forever. That is not that good for visualization purpose. Therefore, instead of that, we have used still periodicity even in this K space. So in this case, we have used that. So please concentrate. This point can be moved into this one, and this point can be moved into this point. So if I just use red color, and that will be the red color. And if I just use different color for this branch, then it will be mapped into this way. So although they are just looking symmetric, but their transition is strictly follow the rule of periodicity. So for example, if we have this number or this branch, and this branch is exactly mapped into that way, because the allowed transition is simply given by this 2 times or multiple over 2 pi over a. So we can move it into that way and also move it in that way. That's the reason why if we just map our electronic states into the first Boolean zone only, then you know now we have this kind of behavior, and there occurred certain differences in their energy level. But please note that why do we have energy difference? Is so the origin of this difference is not actually comes from k equal to 0, and it comes from the difference in here, and the difference shown here is not in this case it's okay because it is occurring here. So please note that any kind of discontinuity in our EK diagram comes from the zone boundary of our K space. Okay, so only when we just map into the first Boolean zone, then that discontinuity can occur in an arbitrary position, not just a zone boundary. Okay. So now let's go to the second part. Up to now, I have tried to why do we have band gap inside our general band structure? The answer is quite clear. Atomic cores are placed in a periodic manner. They generate periodic potential, and when we have periodic potential, then we can have some difference energy levels at zone boundary. That is corresponding to the, in general, the gap inside our EK diagram. EK diagram is sometimes called as a band diagram, and this y-axis, oh, you can find it so I can see it. Oh. Okay, so this y-axis is corresponding to the energy, and this x-axis is corresponding to the k vector. But unfortunately, visualizing this k vector in three-dimensional vector is quite much difficult to all of us. So instead of drawing all points, is every point inside our first three-dimensional Boolean zone, they means that physicists do some more clever way here. Oh, sorry, I cannot see clearly. For example, here in principle we must find out every EK relation in this entire first Boolean zone, but the typical way we do is calculate or draw in that way, starting from this gamma point. So follow certain branch called as X point. There is a highly symmetric point, and there is another point called as L point, and we just follow this branch. So where can you find such kind of a branch-wise drawing? So here we start from gamma point, the origin of the first Boolean zone, and go to this X position, or go to this L position, and just draw in that way. If you ask me, what happens if we have certain position not corresponding to this branch from gamma to X or gamma to L? Of course, there will be certain values and there will be certain energy state, but usually when we draw it, we do not draw them. But there exists. This is just a partial information only for drawing purpose. I mean that in actual calculation we must calculate some points even in not very symmetric point. However, when we visualize this band structure, we usually prefer to have this highly symmetric point. And this is the calculation result for our silicon material. And you know that this is the maximum energy of our valence band. And you know that here we have the minimum energy of our conduction band. So since this is very important to us, so let me just have a look at the magnified version of this one. I just crop it and magnify here. Once again, this point is the maximum energy of our valence band, and here please have a look at it. Here we don't have the maximum point, the minimum energy level. The minimum energy level is laid on a slightly off from our x value. Actually, it is known that starting from our gamma to x happen to be the sorry about that. The minimum energy occurs at just 85% in its journey, starting from gamma. I'm going to the x, and if I arrive at the x point, let's call it as number 1. Then this minimum point here, this point is just 85% of its entire journey. So the minimum conduction band minimum is located close to the x point, however not exactly located at that x point. But you know, this is a little bit more complicated, but let's have a look at this one. You know, how many x points do we have? Is there only one single x point? But you know, this is the first Brillouin zone, and we are now talking about this x point. But we can also find another equivalent x points along the opposite direction, or for x or for z. So we can easily understand there will be 6 different x points in our first Brillouin zone. So unfortunately, when we collect the total number of minimum energy points in its conduction band, we don't have only one minimum point, but we have 6 minimum points, and they have different directions. 2 of them are aligned. For example, we can find 2 whose minimum or whose x position is laid along kx direction, and also we can find 2 laid along ky direction and 2 laid along kg direction. So since they are all equivalent, their energies are the same. However, they have different directionality. So that is one thing we have to understand. Up to now, we are now talking about this conduction band. However, if we go to this valence band, everybody understand this is related with the holes in our silicon material, and you can see that there is what happens there. We have 2 different branches, and these 2 different branches are related with different holes. So holes inside the silicon valence band is not one body. There are substructures inside our silicon valence band, and this branch, which shows much smooth transition or slow transition, this branch is called as heavy hole. Why it is called as heavy hole? So you will see it later. And there you have more steep difference here, and this one is called as a light hole. So heavy and light. And you know, although not written here, there is another one slightly off from its maximum value, and that is called as split of hole, but that is not drawn here. But anyway, the answer, the lesson up to now is, okay, we have now know that every kind of this EK diagram comes from the periodicity of our electronic or atomic system. But when we apply it to the real bulk system like a silicon, germanium or something like that, its behavior is quite much complicated, and every material shows different behavior. Therefore, we must memorize and understand and getting familiar with their individual behavior. In this course, we are more or less almost exclusively involved with the silicon material, so we must understand the behavior of our silicon conduction band and silicon valence band. Okay. Also, there is another important topic. Now, I assume that we can have the relation between E versus K relation. Simply speaking, for every point in the first Brillouin zone, then we can have a function E of K. That is the one we have done in this slide. Of course, if I ask you to do that, but that will take several days. So to study the underlying formulation and doing some computational job, but we don't have to do it right now. Let's assume that somebody did it for us. Now let's assume that we have a well-defined function E of K. Then now my question is, how can we calculate some important parameters for, especially for transport problem, movement of our electrons and holes? In this case, we can define two important quantities of velocity of electron and mass of electron. Velocity of electron, mass of electron. Well, if we are talking about mass, then somebody can say that, okay, mass of electron is defined as m0, and it is corresponding to 9.1 times 10 to the minus 31 kilogram. However, please note that this is the mass of a free electron. If we have an electron which is not fastly moving and without being affected by environment surrounding it, we can expect such kind of mass. However, our electron is not a free electron. Although it behaves just like a free electron, but it is not. It is always affected by surrounding atoms and accompanying electrons. So its effective mass can be highly different from this m0 value. Now let's make an analogy to the human person. So now let's say that in bare person cannot move fast enough. For example, if we have to move 40 kilometers, then maybe even for the very fast man or woman, it takes 2 or 3 hours or 4 hours. However, in our case, if we have to move 40 kilometers, how long does it take? Depending on whether you have a car or not, but anyway, if you have a car, then maybe that will just take half hour. Okay, what happens? We are not just an animal. We are equipped with many different things like a car, cell phone, and human relationship, many different transportation capabilities. That's the reason why we can move even faster than the bare person, just learning quite eagerly. So quite similarly, electron inside crystal system is not a free electron. They are heavily affected by environment, so we can expect different mass. And let's go to the velocity. And in the case of velocity, we can calculate this velocity by the action or operation of partial derivative of our energy. So although I have written in that way, it is quite simple. We can perform the operation like partial derivative of our E with respect to k direction and ky, kg, and here we have x direction, y direction, and z direction. That will give us the velocity of an electron whose k value is just given by k vector. Since E energy is a complex function, complicated function of kx and ky and kg, it is not directly expressed in a simple form, but anyway, by following this operation, so taking the gradient in a k space, we can get the velocity. So simply speaking, once you have energy versus k relation, then now you can answer that the electron locating or having certain k value will move certain velocity given by this value. Okay, so this is important. And another one, inverse mass. Inverse mass means that 1 over m. This inverse mass, unfortunately, it is direction dependent one. I mean that mass is just showing certain quantity. If we exert a force to a certain object, what will happen to its velocity? How the acceleration is calculated? That force and acceleration, that is given by the mass. However, in this case, unfortunately, in our case, it is position dependent. Once you apply x direction, the force is exerted in x direction, then in general, your electron will be accelerated along the x direction. Yes, you're right, but in general, your electron can be also accelerated y direction and z direction. So here we have a double index ij, but this I and j is not 1, 2, 3, but this is a directional component x, y, z. So they are in general, inverse mass is a tensor, second rank tensor, but you know, fortunately we can have many vanishing components. Anyway, the inverse mass is also simply given by this expression. For example, if we calculate inverse mass along x direction, it is simply given by 1 over half r and second order derivative of our energy with respect to kx direction. Okay, then how about yy? If we have inverse mass along y direction, then just takes this operation. We can have this one. So now let's have a look at silicon conduction band example. This example is particularly important because not just one example, but we will heavily rely on this silicon conduction band. So you know, we are fabricating our MOSFET with using silicon. So understanding the silicon conduction band is quite important. So here we have the EK relation of our silicon conduction band near the minimum point. I mean that if we come back to this graph, then can you express all kinds of this complete K-space or complete conduction band with a single analytic expression? It is not possible. However, what we do right now is, since this point is so important and all important transport behavior is just occurring nearby this point, because they have the lowest energy available energy in the conduction band, we wanted to develop a close approximation, good enough approximation for this point. And fortunately, it follows the parabolic behavior. So what we can say is, here we have some strange number like EC, but why do we have EC here? This is the conduction band minimum energy, so it is corresponding to this energy. The minimum energy is written as EC, and now we are describing the energy measured from its minimum energy is given here. Sorry about that, but there is another question on this K. What is K? Actually, K should be measured from, of course, this gamma point. Oh, sorry, this is not F. This is gamma point. Gamma is regarded as 0, 0, 0. However, in this notation, also we say that in locally, this is the origin of our K. Why? Although we have this behavior, and let's say that this is the real global origin, but we are now describing the parabolic behavior only nearby this point. So therefore, we have introduced a local coordinate. Although this is not 0, 0, 0, but for y, instead of this, the real k, just to introduce certain offset, and that is written here as k value. So sorry about that, but this is quite much conventional way. So in the case of conduction band description, the origin of your K is not located at the gamma point, but the minimum point of your silicon conduction band. Okay, although I have prepared more slides, then let's wrap up today's lecture and see you next Monday. Thank you.